Okay, this is going to be the last topic of the semester, and who knows, it might be moved up in the semester in future classes. So if you're in a future class and you're hearing this and say it's the last thing, it's not, but it is right now. So it's called gas laws, and it's going to talk about the behavior of gases. Gases. Now, gases are a little different because the gas laws are a little different because it's really not what I would consider chemistry. There isn't a change, but there's a study of the property of matters, which chemistry also looks at as well. And um, so there won't be anything changed from one thing to another. You'll just get gases. There's some basic assumptions we have to make about gases at the molecular level, or down at the atomic molecular level. And we're not 100% sure if gases behave like this, but by all means, they seem to, based on how we observe them. So here are some basic assumptions, and you don't have to memorize these, but in fact, you'll see at the end of this lecture what you'll need to know from it. But pay attention to it, and it's part of the process. Is as usual, this whole semester. Sometimes I go on about stuff, and I don't know. Maybe some of you just skip to the final couple pages and what you think is important, and you don't listen to my lectures. I can't stop you from doing that, but I just think you always need to have a background to do what you need to do, and an understanding of it, how it applies in the context of it. I just don't like giving you formulas and having you fill things in. I like you having understanding things. And so that's where we're going here. So let's try to understand how gases behave. So here's what comes up: a few assumptions. And like I said, you don't have to memorize them, but hopefully you'll see how this works out. So we consider gases as being very, very, very. The particles of gases are very, very small, almost so small that they don't have any volume at all. Now, you may say, well, if they have no volume, then they don't exist. In some ways, from our big point of view, yes, that's true. But the thing is about it is it says that these points, they may not have volume, but they do have mass, okay? And they move around, okay? And all the gas particles right now, and if you take Chem 121, you'll see we'll change this, is they all have the same mass, whatever the mass that is, okay? And, you could just figure it out. Whatever material we have, we can figure out, like if you have oxygen, all oxygen gas, then all the molecules in the of the oxygen gas have 32 grams per mole. Also, the gases never crash into each other, okay? So they're just wandering around, and they never, they're flying around, and they're never hitting each other, okay? There's no attraction, so if you have a gas particle here and one over here, they don't feel any kind of traction or repulsion with each other. They always move in a straight line, okay? And they have a constant speed. And we'll talk about that speed in a second. They're enclosed containers, okay? So here's your gas particles, and they're closed in a container. And they're randomly spread about in the container. The one thing that's the most important things about this, that we can measure is about a gas, is it does collide with the walls of the container. And when you crash, okay, into the containers, they actually don't lose. We're going to say they don't lose any speed. Like if I threw a ball against the wall, like a basketball against the wall, the ball's not going to come back with the same speed that I threw it, because some of the energy of the ball when it hits the wall loses, the energy gets lost to the wall, and the ball doesn't come back as fast. What we're going to do here is assume that when a gas particle hits the wall, it doesn't do that. It comes back with the same speed. Okay. And there's a reason for that. And it has to do with the outside world, actually. The outside world gives the energy back to it so it can go keep up without losing speed. And what we say is that it doesn't lose momentum. Okay. So when we throw something against the wall like a ball, normally it loses momentum and it'll slow down. But these don't. So we call those elastic collisions. They don't accelerate or decelerate, so if they have a speed, they always keep that speed. When they do bounce off, they bounce off. You don't have to know this, but whatever angle they hit, they come back with it at the same angle. So if you ever played pool, it's like the same kind of idea. If you hit the ball, it's going to reflect back at an angle that's the same kind of angle that you hit it. You don't have to know this down here. All right. Okay, next. So let's look at the container with the gas. So let's look at a container with gas particles. So here's your container, and it has gas particles in it. Okay, the container has a volume, and that's the space, and we can measure that space. Okay, its length, width, height. So we might want to just look at a cube. And a cube has certain height, certain length, and certain width. Okay, and for now, what we're going to do is have a method of measuring how fast the particles move. Maybe like a very, 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 very small radar gun, and we can measure how fast they move. Okay, the other thing we could want to be able to measure is how many gas particles are in here. And finally, the other thing we want to measure is how often it hits the wall. Okay, so how many collisions the gas particles will have against the wall in a certain area. Okay, per unit time. So if you just select one area on one side of the container, and you're going to assume that every space on this container is going to get the same amount of collisions. Is that what you do? Is you measure how often the particles hit that area. Yeah, how often? How many? Okay, collisions. All right, and now out of measure by looking at these four things: the volume, the speed, the number, and the collisions, we can come up with 6 different scenarios. Okay, so here's the first scenario. What we're going to do, and here's the 4 different variables, we call them: number, collisions, volume, and velocity. And what we're going to do is we're going to start out with a certain number of particles in our container. 1, 2, 3, 4, 5. We know the size. The volume is 3, and it doesn't matter units, okay? And each particle has a speed of 4. Okay, so each particle is moving 4 whatever units. The whole volume of this thing is 3, and there's 5 particles. Okay, now what I want to do is look at these relationship between the number and collision. So what I want to do is I'm going to increase the number of particles and keep the volume and the speed constant. So the size of the box stays the same and the particles are moving at the same speed. But now I'm adding 10 particles. Okay, so I have 5 more particles. What's going to happen to the number of collisions? Okay, 5 to 10 here. So that what's going to happen to the number of collisions? I hope you can see that they increase because you have more particles. So now you're going to have 20. Okay, so what you'll notice is that the more particles you add, the more collisions you got. Okay, and so you can come up with this graph It's simple, okay? And you've seen these types of things before, where y equals mx plus b, okay? All right. In this case, there's the y-intercept. There's no, that doesn't exist. And so y is the number of collisions. Okay, m is our slope, and x is our number of particles. Okay, I'll just call n, number of particles. We'll call it n. Sorry, and we're not going to use m. We're going to use k. All right, and we'll call it k1. So we're going to say that the number of collisions is related to the number of particles by, okay, the number of particles, n, by some constant k1. Okay, and this is a linear, directly proportional relationship. So as you change the number of particles, the collisions go up or down according to the change in particles. Okay, so this is our first formula, and I hope we can see this graph, how it works. Okay, second scenario. Now what we're going to do is look at the velocity and the number of collisions. So now you have your box, okay, your before and after box. And before you have 1, 2, 3, 4, 5. And after you have 1, 2, 3, 4, 5. And the volume of the box is 4. Okay. But what you're going to do now is you're going to change the speed of the particles. All right. So now what we're going to do is we're going to triple the speed of the particles. What's going to happen to the number of collisions? Okay. Well, I hope you could see that the number of collisions go up to 30. Okay. The only thing we changed is we didn't change the number. The last example we changed the number. This time we just changed the speed. And now we get a change in collisions. It goes up as well. Okay, and then what we can do is we can come up with a similar, as we just had a couple slides ago, is that the number of collisions is equal to some constant. You call it the slope. We'll call this K2 because it's different than the K1 we had before, times the speed of the particles. All right. Okay. All right, now let's look at scenario number 3. Okay, so again, we have two boxes. And then both boxes have 5 before and after. Okay, the speed of the particles is 4, whatever the units are, before and afterwards. Okay, but the thing we're going to do is we're going to change the size of the box. We're going to make the box bigger now, okay? All right. So, and what we want to do is what happens to the number of collisions. So we change the box from 4 to 8. What happens to the number of collisions? Well, the speed stays the same, so it's going to take longer for these particles to reach the walls, and so the number of collisions is going to go down, okay, because the volume gets bigger. So in this case, so now it's 5. So when you increased the volume, now the collisions have gone down. In the previous two examples, it was the opposite. Whatever you so in terms, if you increase the speed, the collisions go up, and if you increase the number of particles, the collisions go up. But now, when you change the volume, when it goes up, the collisions go down. And if you did the opposite, if you decrease the volume, the number of collisions would increase. Okay, so if you could just think about it, now there's particles that have less time to get to the to the corners, and you can get more collisions. So what does that look like? So this is going to look something like this. It's not going to be In the previous two examples, as you increased one, the other one went up. In this case, as you increase the volume, the collisions go down. Okay, and we call this an inversely proportional relationship. And this equation can be written as the number of collisions is equal to some constant, and it's the slope, and it's a more complicated slope, but you don't have to worry about that, divided by the volume. Okay, so if you increase the volume, okay, so one is, the number of collisions will go down, and this equation shows that. So we have three equations so far. The first one was K1 times number, and this is directly proportional. The second one is number of collisions directly proportional to the speed. And now we have the number of collisions is indirectly or inversely proportional to the velocity. Okay. So we are halfway there. Three more. Okay, scenario number 4. Okay, scenario number 4, we have our box still. And we have 4. All right, it's 4 guys in each box. But, okay, in number of collisions, so we started with 5 collisions per whatever, okay? And then, in this initial box is 5, has a size of 5, and each particle has 4. And so now what we're going to do is that we're going to increase the velocity of the particles. But the key thing is here is we got to keep the number of collisions the same. Now, remember, if we increase the velocity and we had volume constant, the number of collisions would go up, okay? And that was the second relationship we had that I just showed you. Now, but we don't want to increase the collisions. So to make sure the number of collisions keeps the same, what do we do with the volume? Well, we increase the volume, all right? So now we would double the volume, okay, because if the velocity increases, the collisions will naturally want to go up. But if we increase the volume, we can see that that'll keep the collisions the same. So, so if you want to keep the collisions constant, and this is key here, all right, and you change the velocity, so in this case we increase the velocity, what do you have to do? The speed, we could call it. Velocity and speed are the same for us. So if you increase the speed, the volume's got to go up as well. Okay. All right, and then we get, just like the very first two examples, as you increase one, the other one increases as well. So if you increase the speed, or velocity, we call it, you have to increase the volume to keep the collisions constant. And so you have this equation. So far we have 4 equations that are directly proportional, and then we have one that's indirectly proportional. Okay, number 5. Number 5, we want to keep the number of collisions constant, and we're going to keep the velocity constant, so or the speed. So let's say the collisions is 5 before and after, and the speed is also constant for before and after. All right. But what we're going to do is we're going to double. We're going to take to start out. Okay, we're going to, let's say we have 5 particles, and then what we do is change the particles to 10. Okay, and let's say the initial volume was 2. Okay. All right. Now, if we doubled the number of particles and we want to keep the number of collisions constant, what do we need to do the volume? We need to increase it, just like in a previous example. So if we double the number of particles, we have to double the volume to keep the collisions constant. Okay. So now what we got is, again, a direct relationship. Number of particles increase, the volume has to increase to keep the number of collisions constant. And here we go. And this is our fifth equation. Okay. Again, it's directly proportional. As you increase the number of particles, the volume has to increase to keep the collisions constant. All right, our final example. This is, again, we start out with the box. And let's say what we're going to do is we want to keep the number of collisions constant. So let's say our initial collisions is 5, and our final is 5 as well. And our volume is going to be constant as well. Let's say the volume stays 5. So I have a box before and after. The box stays the same. Okay, but what I'm going to do is change the number of particles. Let's say I start out with 5 particles and end up with 5 particles. Okay, actually 10 particles. So let's say I go from 5 particles, and it's 5 here. And number of particles over here is 10. Okay, but I want to keep the number of collisions constant. Okay, so they have to have the same number of particles, same number of collisions in both cases, but I have more particles here. Well, the volume's the same, so the only thing I could do is change the speed. Okay, so if I increase the number of particles, and I kept the volume the same, we would expect the number of collisions to go up, because they're hitting more often because you got more particles. That was in the second scenario. But now we don't want to have that. We want to keep the number of collisions constant. So what we've got, the only way you can do that is decrease the speed. Okay. So in this case, to keep the number of collisions constant, if you increase the number of particles, you have to decrease the speed. Okay, and so this is like the third scenario where we had an increase causes a decrease. Okay, and you get something like this. And this is inversely proportional. So if you increase the number of particles and you want to keep the number of collisions constant, you got to slow down the particles. All right, so there's our 6 scenarios. Okay, and I hope you got them and sort of understand the principle behind them. You don't need to memorize them. You don't have to do any math. Okay, I just hope you see how these graphs and how you came up with these equations and how they make sense. So now what we're going to do is take a look at the big picture a little bit. Okay, so we have our 6 equations, and here's just something I want to do before I get into relate. So right now we're down at the very, very small molecular level, or say we have a little tiny radar gun, and we can measure the speed, we can count the number of particles and things like that. It's kind of cool is that you can actually put all these equations together into one equation. The simple thing in math is that we can combine all these equations and make one giant equation like this right here. And you don't have to know how to do it, but we get this thing here. Okay, this is all these k's here. All right, just rearranged from the 6 scenarios. And then we get this equation here. And again, you don't have to know how it's done. Then you can cross things out, and there's a C here and a C here and a V here and a V here and so forth. And what you end up with is this thing here, which is one giant constant now, because All these are constants, and so this is just one constant. And then we're going to call that constant little r is equal to this, CV divided by NS. And this is actually going to turn out to be a pretty important thing, okay? What this says is that the number of collisions times the volume is equal, divided by the number of particles times the speed is always going to be equal to some constant, no matter what. Okay, so it's just going to be solid. Okay, and we'll put this in perspective in a few. All right, now the human world. Now it turns out we don't have a really tiny radar gun that we can measure the speed. It's hard to actually measure. I mean, we learned about counting particles. It's really hard to count particles because there's so many of them. So we really can't do that directly. Okay. We can measure the volume of something. We can measure that. We can definitely measure how the space that these particles in. And it's also hard to measure how often they hit the walls. Okay, the number of collisions, things like that. In the big world, okay, if we have a box of gas particles, we can't sit there and count the number of times it hits the wall. We can't count. We don't have a tiny radar gun to measure the speed, and we really can't count all the number of particles because there's so many. So how do we do this? Okay, how can we do this in the big world? All right, so here we go. So volume is easy. So the volume is whatever. We can measure the volume, length times width times height. All right, so that's fine. Okay, now the speed of the particles. Well, you can't directly measure the speed of a particle, but you can do, based on this guy here, his name is Ludwig Boltzmann, a guy in the 1800s, early 1900s, found out there's relationship to the speed of gas particles and their temperature. Okay, so if you increase the temperature of a particle, it's going to increase the speed. So you don't need, so because of this, and there's an equation for it, so if you know the temperature, you can know the speed. So instead of, and we can't measure speed because we don't have our little radar gun, but we can measure temperature. Okay, so we're not going to measure speed like we did in our scenarios. We got to measure temperature, but we know from temperature we can get speed. Okay, the number of particles we know is related to moles. Okay, so again, and we can figure out moles from grams. So we can measure them. So we can't measure moles directly, but we can measure its mass, their mass, so we can measure it, the weight of a gas, and then we can figure out how many particles in it. Okay, number of collisions, and this is one that takes a little bit of time, and I don't have to go through it with you, but you can take a look at it here if you would like, and in 121 we go in more in depth of it. But it's simple, is that the number of collisions can be measured simply as the pressure of a gas. All right, so if so you may have heard of PSI, okay, which means pounds per square inch. That's the pressure, okay. Like your tire, you can measure how much air pressure. Air is gas, so when you're measuring your pressure of the air pressure in your tire, you're measuring the gas pressure in your tire. And really what you're doing is you're measuring how many collisions that are taking place per area per time. Okay, so what we have is we have so volume we can measure. Speed we can't measure directly, but if we measure temperature, we can measure speed. Okay, we really can't count number of particles directly, but if we weigh it, we can figure out how many moles. And we can't measure the collisions directly, but if we know the pressure, we can figure out the collisions. So what we're going to do is we're going to change our our constants. We're gonna keep volume the same, because that does change. But instead of using speed, we're gonna use temperature. We're gonna use moles for number, and instead of using collisions, we're gonna use pressure. So what we're gonna do is change our equations to reflect this. Okay, so here we are. What I just told you. So instead of using speed, we use temperature. Instead of using collisions, we use pressure. Okay. So now what we're going to do is change equations. Like the very first one we had is the number of collisions was equal to the number, some K1 times the number of particles. Okay. So now what we're going to do is we're going to replace collisions with pressure. So pressure will equal K1 times N. Okay, and what we got is our 6 equations that we determined. Now we're going to replace the collision C with P, and speed with temperature. Okay, and we get these equations here. And these are going to be related to people that actually discovered these relationships. They didn't know about the small world. They actually just did experiments and they came up with these relationships. Each one of these relationships is attributed to, first one was attributed to this guy named Dalton. This one is Gay-Lussac, Boyle's, Charles, and Avogadro. And actually no one is actually associated with this name. I don't know why, but all right. So let's be more specific. Okay, so what we're going to do is now we're going to not look at all 6. We're going to look at just 4 of these guys. All right, and what you can do with a little bit of math and algebra and things like that, you can change each equation to look differently. Okay. So Gay-Lussac's relationship on the previous slide says is that the number of collisions or pressure was going to change according to the temperature. All right. Okay, so this was Gay-Lussac's law. Okay, I forget what the constant here, if it was 2 or 3 or whatever. Okay, so what you can do is you can mess around with this guy, and what you can do is get this equation here. Now, what does this mean? Okay, what this means is that the initial pressure divided by the initial temperature is going to equal to the final pressure divided by the final temperature. Okay, so 1 stands for beginning and 2 stands for end. Okay, and through a simple math, okay, you can rearrange this equation so it looks like this. All right, for 110, what I want you to do is when you see Gay-Lussac's, use this equation. Okay, same thing with Boyle's. Again, Boyle's law was the pressure was inversely proportional. I think it's K3 over V. Okay, what you can do is rearrange it and come up with this equation. What this says is that the initial pressure times the initial volume equals the final pressure times the final volume. Charles' law, you'll get this. Okay, and that was the volume changes according to the temperature. Okay, again, you can through some algebra you can come up with this. Okay, but actually I want you to use this one here because it'll make your math world easy. And then finally, the last one was the volume changes by some constant times the number of particles, and you can get this relationship, but you can change it to this formula. And these are your 4 formulas that there's one more formula, which I'll show you in a minute, which relates to something I went over a couple slides ago. But these four formulas and their names. Okay, and I'll show you how to use them in the next PowerPoint. Okay, let me go back to a slide where, remember this equation I came up with? I don't know, it's like 4 slides ago. Okay, well, we can do that. We can replace C with P. We can replace S with T. And we do that, we get this equation here. And this equation here is actually a big deal in chemistry and physics. It's called the ideal gas law. And you can rearrange it so it looks like this. PV equals nRT. And R is a constant, and I'll give it to you. It's and it changes depending on units, but it's constant. And it's called the universal gas constant because we think it's true everywhere in the universe. Okay, so here you go. So that's the basic structure for gas behaviors. In the next PowerPoint, we're going to talk about how to use the formulas for Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law, and the ideal gas law. And I'll give you examples of each one. And the test that you're going to have is going to be a small test, and it's going to relate to these five laws. Okay, and you'll have problems that look very, very, very similar to the examples I give you. All right, so on to the next slide, which gives you the problem.